Hello everyone. Today we want to talk about the 4-bit up counter and see how we could design a 4-bit asynchronous up counter. So as you see, it's clear from the name whenever you are talking about the 4-bit counter, up counter. So definitely you need to have 4 outputs, and also you have one input, which is your clock. So whenever your counter actually see the falling edge, rising edge, depend on your counter, it's actually count that falling or rising edge. For example, if you have the falling edge, whenever you are here, it should be count 1. Whenever see the second falling edge, should be count 2, 1, 2, and next should be 3. So let's see how we could design that. So as you could see here, so we use actually 4 T flip-flop. So as probably you know, the T flip-flop, whenever you give a 1 in the input, usually it's toggle the previous state or condition, and whenever the input of the T flip-flop is 0, it's just hold. So we use actually 4 T flip-flop. Their input is just 1. We actually connect the output of the first one to the clock of the second one. So the output of the second one is a clock for the third one, and the output of the third one is the clock for the fourth one. So you see these 4 is our output. We have one initialize input, which is connect to the clear inputs of the T flip-flop. As you know, whenever the clear input is active, so this condition of this flip-flop will be 0. We connect all the clear pins together and just call that initial input. So that means before you start you working with your counter, you just need to active these inputs, which is you active that with 0. So that means I'm going to start my counter, so I active these initial input, so it's connect to the clear, you active that by 0, so that means you actually put the 0 inside these 4 flip-flops. So that means you made this first actually for a 0, which is should be 0 whenever you have the up counter, right? The up counter start to count from the 0 and end up with 15, right? You have 4-bit, the biggest number you could have with 4-bit is 15. So that means 4-bit up counter start to count with the 0, 1, 2, and end up with 15 whenever see any of these falling edge. So here our flip-flop is sensitive to the falling edge, so that means you active these initial input, you have the 0, so then whenever it see the first falling edge, it should be go to the 1. Whenever it see the second falling edge, should be 1, the next should be 2, the next falling edge should be 3, and whenever you see actually the last one, that means the 15th falling edge should be 15, and then again it should be back to the 0. So this is a design of the 4 bits asynchronous up counter. So let's see why it should be work. So I start with checking the first bit, which is x0. So whenever you start to count to 0 to 15, if you just consider this column, which is bit 0, so whenever you active these initialize, this is 0, in the next falling edge should be 1, in the next falling edge should be 0, the next falling edge should be 1, again 0, 1, and 0, 1. So let's see if these first flip-flop able to make this first column. So you put this 1 here as an input, so definitely it's just toggle. These flip-flop just toggle because the input is all the time 1. So you connect the clock pulse to this one, so that means you active the initialize, you have the 0 here. So then in the first falling edge, it's take a look to the input is 1, is toggle that. So you are on the 0, toggle of the 0 is 1. So in the next falling edge, so you have 1, its toggle will be 0. In the next falling edge, it should be toggle, it should be 1. in the next its toggle will be 0, and you see, yes, it's actually produced these exactly these column that you see these for the first flip-flop. So next, to check the second column and see the circuit able to make the second column, which is x1 or not. So again, we check with the first, you active the initialize in the beginning of your counting, so that means you have the 0 here in x1, right? So then in the first falling edge that it see, it's actually don't take a look to the input, because this is not the falling edge. If you check the clock pulse of the second flip-flop, it's connected to the x0. So that means this first column x0 technically is the clock pulse for this x1. So that means whenever this clock pulse, actually this x0 is falling edge, the flip-flop actually take a look to the input, it is 1, it's toggle. Otherwise, that means whenever this clock pulse is not in the falling edge, it's not doing anything, it's just hold. So that means you are here 0, check the clock move from 0 to 1. Moving to 0 to 1 is not the falling edge, that's rising edge. So that means you just hold that. So that means the next one should be 0. So then you take a look to the clock pulse, which is this. It's changed from 1 to 0. Changing to 1 to 0 is falling edge. So it's take a look to the input. It's 1. It's toggle that. So I'm in the 0. If I toggle, I'm actually in 1. And then it's actually repeat that pattern. So that means here I'm in the 1. That's not the falling edge. It's hold. You have 1. So then it's actually toggle whenever you have falling edge. That means whenever the x0 change from 1, 0, it's toggle. If you check all of them, here it's toggle, it's moved from 1 to 0. Same thing for all of them. Here you toggle, it's changed 1 to 0. And again, here you have toggle whenever you move from the 0. If you check the clock pulse, you see it's moved to the 1 to 0. So that means the second one definitely produced the second column that you see. Check the third one. So the clock of the third one is x1. So that means x1, this column is the clock for this output. So definitely the input is 1. Whenever this is the falling edge, it will be toggle. Otherwise, it's going to be hold. So whenever I active this initial, it's actually 0. I'm in this case. So then check here. You move from the 0, 0 is not actually the falling edge. It's hold. So I have 0 again. Change 0 to 1 is not the falling edge, it's hold. Again, I have 0 here. 1 to 1 is not falling edge, it is hold. So see, when you need to toggle, here you toggle, you need to toggle. If you check here x1, which is the clock pulse for x2, you see definitely this is actually a falling edge. Here you move from 1 to 0, it's a falling edge. You take a look to the input, which is 1, it's toggle. So that means it's changed from the 0, 1. Same story here to here, there is no actually the falling edge, it's hold the 1. So here it should be toggle. If you take the clock, it's happened 1 changed 1 to 0. That means it's actually falling edge. So that's the reason it's actually toggle. You have the 0. Same story, it's hold. So whenever if again is the falling edge, which is change 1 to 0, again is toggle and hold in that state. So that means definitely this produce this actually the third column. Take a look to the x3. If you take the look to the fourth flip-flop that you have, the clock pulse of that is this x2. So that means this column is the clock pulse for this x3. So that means you check whenever in the beginning you active initialize, that's 0. So then take a look this and see when falling edge happen, and then it could be toggle because the input is 1, right? So here 0 to 0, no falling edge. So for that reason, all of them is 0, because here to here is never changed from 1 to 0. So here it's changed from 1 to 0. That means it is falling edge. Here it's take a look to the input is 1, it's toggle. So you are on the 0, you change in the 1. Again, in the all of these cases, it's not actually falling edge. For that reason, it's hold. So that means it's actually prove that this circuit that you see here definitely is one 4-bit asynchronous up counter. So the reason this is asynchronous, because the clock pulse is not actually connected to each other, and each of these flip-flop has the separate clock pulse, so that means they are not actually the synchron. The synchron happen whenever you actually connect these all clock pulse together and have one single clock pulse, so that means that all of them actually work in the same phase and the same time that actually change their condition. So let's to simulate this. So if you simulate this in the multisim, so this is actually the simulation of that in the multisim. So I use the JK, which is, the T flip-flop actually is a JK flip-flop, which you connect the J to K and the label that has a T, right? So see, the all of them is actually somehow is a T flip-flop, but I use the JK, just connect J to K and call that T. So this is exactly what you actually have here. So is exactly the same circuit. So as you could see, the T input is 1, so I connect all of them. J connected to K make the T input, and all of them is 1. So I connect all of them to this VCC, which is 1. So these are your output, which I put the indicator, which I see when this is 0 or 1. So the clock, so see, this is actually the falling edge flip-flop. So the first one connected to the clock pulse, which is this is a function generator that produces your clock. You could actually change the frequency of that. Whenever you change the frequency of that, that means you're able to count faster or slower, depending on your needs. So the first clock pulse connected to this, which is the produce the square wave or your clock. So then see, similar with our design, then this one connected to the clock of the second one. So these output connected to this clock, and this is connected to the clock. So exactly similar with what we did. So this is actually the initialization. So see, I connect the all clear inputs together, and with the switch, whenever I want to active, which is you are active with the 0. So that means in the beginning, you just connect this to the 0, then back to the VCC. So then it should be start to count from 0 to 15. So let's do that. Let's start to simulation. But again, I start with the actually initialize that everything is 0. So right now it should be start. So this is actually 1. So then should be 2. Then in the next actually falling edge should be 3. So then should be 4. So this is 4. So then should be 5. These two should be on. So this is 5. So then should be 6. These two should be actually on. This is 6. The next should be 7. So these 3 should be on. The next should be 8. This should be 1. The all should be 0. The next should be 9. This one and this one should be on. That's right. So the next should be 10. So 8 plus 2 is 10. That's right. The next should be 11. So this is 8, 2, 1, 11. That's right. So the next should be 12. These two is 12. This is 8 plus 4 is 12. The next is 13. That's right. 12 plus 1 is 13. The next is 14. That's right. 8, actually 4, 2. That's right. And the last one is actually 15. Then it's actually back to the 0. See, it's actually back to the 0, and again start to count. So if we want to do actually be 1 second, so let's just change that to the hertz. So if I change to the 1 hertz, so this is actually the frequency, right? This is not the period. So that means the period is 1 over f. So if I put 1, so the period will be 1 over 1, should be 1 second. So that means the period between two falling edge is 1. So definitely should be count every 1 second, right? So let's test that. I change that to the 1. So then I simulate that, and let's see what's happened. Yeah, see, this time is more faster, right? It is 1 second. So it's actually, you see, it's actually, you count faster. So definitely depend on your needs. So just be careful. The period is 1 over f, right? So if you want to have more faster, so definitely you need to increase your frequency, right? So if you want to actually have more slower, you need to actually have more small frequency. Even you could actually check this. If this is 1 hertz, let's actually have 10 hertz. I hope I could see the different cases. Just to try this. So yeah, see, that's actually very fast. Probably we couldn't see that. Yeah, see that's too fast. We couldn't see that. So that to do just 5, not 10 is too much. We couldn't actually catch that. So to change to the 1 hertz. So simulate that. We put actually initialize that back here. Yeah, it is. Yeah, see you. It's actually more faster. Yeah, probably the 1 hertz is the best one, at least to observe that's counting from 0 to 15. So I actually keep on 1 hertz, which is, I guess, which is the best one. Okay, it is 1, 2, yep. So that's actually its count. So this is actually simulation. We actually have the output is the binary. So if you watch our other videos, we have one video which I explain how you could convert the binary to the 7 segment. So what I did, I actually connect this counter to the binary to 7 segment converter because I want to see these numbers 0 to 15 on 7 segment. I don't want to see the binary numbers. So if you, I probably have that here. Yeah. So this is actually the same thing. Whatever you see on the left is the same circuit, and this circuit is the circuit that I explained in the binary to 7 segment code converter. If you check our previous video, I have one video which they explain the whole thing. So that means I just connect these 4 output that we have, which is the binary to 7 segment actually code converter. So that means whenever your counter start to count, I'm able to see on my 7 segment. So let's to change this frequency to the 1 hertz because we actually saw the 1 is the best one, at least for observe that counting from 0 to 1. I put on the 1 hertz and I need to back here, stop the previous simulation, then back here and start to simulate that. So first I need to put that 0. See, whenever I active these initialize for a small in the short time it's 0, it's back to the 1, then it should be start to actually count. So see, it's actually count 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, back to 0, right? Again, it start to 2, 3, 4. So definitely if you change this frequency of your clock pulse, definitely you are able to actually count faster or slower with adjusting this frequency of these clock pulse that you have. So I hope you enjoy this video. If you like this video, please actually don't forget to subscribe the channel to support our videos.